Hi, everyone. Hey, let's go over acids and bases one more time for this introduction to chemistry class. We've seen acids and bases a couple times already, and it's come back up again. It's such an important topic. Here's some fine points and some review that we've seen before. Okay, so acids and bases. I forgot to turn on my pen. Sorry, there we go. Okay. This is mostly review. Oh no, there's some new stuff coming in here too. Okay, just to make sure we're all on the same page. There is an older definition of acids and bases called the Arrhenius Definition, and that states that acids are substances that produce hydrogen ions. And remember, that's essentially a proton, right? Hydrogen's the first element. Element number one on the periodic table has one proton, one electron. And if hydrogen loses its one and only electron, you simply have a proton. It's not even a full atom. Okay, so acids produce those protons, H plus ions, when they dissolve in water. Bases, however, produces hydroxide ions. Now that's not a complete definition, but it got us started when early chemists were thinking about acids and bases. Bronsted-Lowry came along and improved on the definition. Acids are molecules that donate H plus. Bases are molecules that accept those H plus. And what that does for us is allow other molecules other than hydroxide ions to be bases. Cool. So anything that accepts an H plus makes a covalent bond to an H plus, that is now acting as a base. Okay, so we've seen those definitions before. Here's something, perhaps it's new. We saw in an earlier video definitions of strong electrolytes and weak electrolytes. So we're going to use those terms here. Strong electrolytes are molecules that form ions. All of them dissolve in water and they separate into ions. Molecules that are weak electrolytes, some of those molecules fully ionize, fully become ions, but other molecules stay dissolved in solution as intact molecules. Okay, so if those electrolytes, molecules that form ions, either all the way or just a few of them do it, if they happen to be acids and bases, then we create strong acids and bases if they're strong electrolytes, and we have weak acids and bases if they're weak electrolytes. Okay, so that's it. Strong acids are molecules that all the molecules all release H plus, they all donate H plus. Weak acids are ones that, some of them fall apart to ionize and others remain intact. Okay, it's important in this class to memorize the 6 strong acids. And I got in parentheses, you should also memorize the strong bases, but they're easier to remember. Let's do those first. If you have the alkali metals, so if you had the periodic table, which I should have uploaded, column 1 has lithium, sodium, potassium. And if you pair up the first column, alkali metals, with hydroxide ion, those are the first of the 6 strong bases. So you're just looking for OH. And then if you go to column 2, the alkaline earth metals, calcium, strontium, barium, okay, those pair up with hydroxide, 2 of them, right? Because the alkaline earth metals form +2 cations. So the balance of charge, you need 2 hydroxide ions for each one of those alkali earth metals to make a stable compound. Anyways, all 6 of these have hydroxide ions. You'll look at them and say, hey, there's an OH group there. Those should be strong bases. So I don't think you necessarily have to memorize this list. Just remember, put an OH group in it and it's probably a strong base. These, however, are more important to memorize. If you go to column 7 on the periodic table, you got chlorine, bromine, iodide, not fluoride. It's weird. Doesn't form a strong acid. But HCl is found in the stomach acid. Yeah, that's a strong acid. Helps us with our digestive system. HBr, HI, same column. They're acting similar to each other. Those are 3 of the 6 strong acids. And then we have perchloric acid. Hopefully you still remember your polyatomic ions. This is the perchloric, This is perchlorate. Perchlorate ion, there we go. So if you know that, hopefully you do, memorizing the polyatomic ions, then you can say, hey, if there's an H plus in front of it, that's perchloric acid, perchlorate, right? And then NO3 is nitrate. And so HNO3 is nitric acid. And then SO4 2 minus is sulfate, sulfate. So we got sulfuric acid. Okay, so it is important to memorize these 6 strong acids. And for me, remember it's the halides for 3 of them, chlorine, bromine, iodide. And then you have to kind of remember, okay, what's the other 3? Perchloric acid, nitric acid, sulfuric acid. So maybe flashcards help. Maybe you can find an app on your phone, kind of help you. Oh, more terms and definitions. So if we look at these acids, remember that old clue we had before, that hint that said, hey, if the chemical formula begins with an H, it probably is an acid. Yes, all the chemical formulas begin with H. And then sulfuric acid actually has 2 H's in the front, which means both of those can be donated. So there's a term for that. Hey, sulfuric acid, you like to produce 2 H pluses, and an H plus is a proton. So we got a word for you. You are a diprotic acid. Di meaning 2, protic means proton. So a 2 proton acid, H2SO4, cool. And then what are you going to call the other 5? Well, they all donate 1. Mono is the prefix for 1. So monoprotic acids for the other ones. H3PO4 is another acid. It's not on the list. So this one is going to be a weak acid. And what's the name of this? Well, PO4 3 minus is phosphate. So this is phosphoric acid. Not one you had to memorize. I won't write the name in there. But from the polyatomics, you should know phosphate. And then what kind of acid is this? Monoprotic, diprotic? Nope, triprotic. There you go. That's all you do. It's a triprotic acid. Anything else necessary? Oh, we'll get to that in a second. Okay, I don't think there's anything left in this column. Let me double check. Nope, okay. Time for us to make a few notes. Okay, strong acids are strong electrolytes. That means all these molecules, once they get in the water, they fully dissociate to form ions. Okay, so we start at the top with perchloric acid. You add some perchloric acid to water. For a second, it's all in aqueous solution. And then there's water around, and it turns out water will react. Well, this is such a strong acid, the water's forced to accept an H+. And so perchloric acid reacts with water, and you get the perchlorate ion. So what became of this? It lost an H+, it donated H+, that's an acid. The other molecule must pick up an H+. So hey, oxygen, you got 2 H's initially, afterwards you have 3. And that H came over bearing a positive charge, and water, you're neutral. So the plus charge is still there when water accepted H+, right? That's a definition of a base, a molecule that accepts H+. And you know this molecule as the hydronium ion, if you remember your polyatomic ions. Okay. So what I need you to know is to be able to predict products of acid-base reactions, just use the definitions, right? So you'd have to realize that, hey, both these molecules start with an H. They both could be acids then. We will have an example where water acts as an acid later, but water's not on this list, so it's not a strong acid, therefore it's weak. This molecule is, so you might be saying, hey, I've never seen this before, but I know that when H is listed first, it's an acid, but both of them have H listed first. Which one is going to be the acid? The answer is the strong one, which is why you need to memorize this list. If one of these 6 shows up as a reactant, you know that's the acid. Okay, and acids donate H+, forcing the other molecule to accept an H+. That's the definition of a base. Donating H+ is the definition of an acid. Cool. And then we get these two byproducts. And actually you get a cation and an anion. So technically you could say that's kind of a salt. Maybe. I don't know. Hydronium, yeah, it's still ionic materials. You should also think of hydronium as reacting, I'm not saying this correctly, like an H+. So if you see the product of a reaction and the product is hydronium, know that that's a strong acid too. H+ binds to water to form the hydronium ion, but water is such a stable molecule, this actually kind of acts like a strong acid. It is. Think of hydronium as equivalent to H+. If you see hydronium, say, hey, there's a bunch of H+'s around. If there's an H+, well, that is an H+. There's a bunch of H+'s around. We're going to use this concept when we look at pH, a measurement of how strong something is acidic. Okay, so just think of H3O+ hydronium as the same as H+. All righty. What else do we need to do? Let's say you see a different acid. So here's the acid found in vinegar. This is acetic acid. You might recognize C2H3O2 minus as acetate ion. Yeah, one of the polyatomic ions. Yep. Okay. So I think I would have to tell you in this case that the acetic acid is a little bit stronger than water. You would say, hey, both of these begin with an H. Maybe both of them is going to be an acid. Well, it turns out in this case, I'd have to give you the information. The vinegar component is a stronger acid than water. So this is going to be the acid. It's actually called, the name of it's called acetic acid. And then that's going to force water to be the base again. However, is acetic acid one of the 6 we had to memorize? No, it is not. Therefore, it is a weak acid. It's not on the list. It must be weak. That's why we have to memorize a list of 6. And now we don't use a single arrow. We're not, so if it's a strong acid, all the acid molecules release H+. If it's a weak acid, then only some of them do it. We set up a reversible reaction or an equilibrium reaction. I can't spell. There we go. Equilibrium or reversible reaction. And that's where sometimes acetic acid will release an H+. It goes to water to form hydronium. When acetic acid releases H+, the resulting fragment is then the acetate anion. And then where did the H+ go? It goes to the base that accepts it. So hey, water, here's another hydrogen. You now have 3, and there's a plus charge as well. And then it turns out that sometimes hydronium gives the hydrogen back to acetate. Acetate then acts as a weak, is it a strong or a weak base? There's no hydroxide ion here. So this is actually a weak base. And we're following the backwards arrow then. We're saying, hey, let's think of this molecule and this molecule as reactants. And we go backwards to form these things, which are then will be considered the products. And that's what happens in a container of vinegar. In your Italian seasoning, Italian dressing, so a mixture of olive oil and vinegar and other herbs and spices. The vinegar, not all of them separate. So yeah, it's tangy and it's tart, sour. So your tongue knows, hey, this is acidic, but thankfully not all the molecules, only about 5% of them or so. Only some of them, a few of them are releasing H+ to create the strong acid. So yeah, So it can sting if it's on a, you know, if you have a scratch or something, if you pour some vinegar, ouch. But if it's in your mouth, it's like, oh, it's sour. I mean, it tastes the salad dressing, tastes good. Anyways, weak acid, not all of them release, and the reaction reverses. Ooh, so it turns out we got the acid here. This molecule is an acid, giving an H plus of this molecule, which acts as a base, except H plus, and then you turn back into this molecule and that one. Is it time to introduce that concept? Yeah, let's do it now. Good. If you're going backwards then, now we have an acid and a base making these products. And if you go forward, right, where we started, you start with an acid and you add a base, you make these products. So there's a connection between the two. And scientists, you know, every new idea gets a new term, a new word. So these two molecules are related, right? This acid produces this base. This base produces this acid. Okay, so there's a word for saying, hey, this molecule has a related partner on the other side. We call that the conjugate. So we have, let's change the color. Can we do that? We have an acid here and its conjugate base. So acetate is the conjugate base of acetic acid. Water has its conjugate acid because you start with the base. The other thing must then be the acid. So this molecule, hydronium ion, is the conjugate acid of water. Okay, so if you're ever asked a question involving the word conjugate, write out the reaction. Go to the start and identify, well, who's the acid and the base and what became of the molecule? So what became of C2H3O2? Oh, here it is. It's just by itself as an anion. So there's its conjugate. Now, is this a conjugate acid or a base? Well, look and see what it does when it goes backwards. Hey, acetate, what do you do when you follow this arrow and you go back here? Hey, wait, you gained an H. Acetate, you accepted an H plus. If you accept an H plus, that makes you a base. Therefore, this molecule must be the conjugate base of the other molecule. We'll do this a couple more times with some other examples, because I remember being a student, it took me a while to get comfortable with the word conjugate. Oh, one more idea before we move on to the bases. Up here we have our 6 strong acids that we have to memorize. One of them is diprotic. It turns out, and here's some information you should know, that only the first hydrogen is a strong acid. The second one is weak. So let's summarize that. H2SO4 is a diprotic acid. H2SO4 is a strong acid, meaning that all the molecules of H2SO4, put it in the water, got some water there, it is strong. So a single arrow, because all of these are going to ionize. Turns out only the first hydrogen falls off completely. So this is an acid, because we had to memorize it, so on the strong acid, so donate H plus, pour water, you're the only thing in the solution that can be the base. So you pick up an H plus to become hydronium ion, and we only do it one at a time. So there are 2 H's, but the first one comes off, leaving behind one hydrogen still stuck to sulfate, and the polyatomic ion, this polyatomic ion is on the list. It's bisulfate. It's also called hydrogen sulfate. got a -1 charge. That's something we had to memorize from the list of polyatomic ions. And then, hey, water, you picked up hydronium. Sorry, you picked up an H plus to become hydronium. There we go. And so that's a strong reaction. All the sulfuric acid molecules separate to become bisulfate ions. Hey, so what's the conjugate something of sulfuric acid? Well, what became the sulfuric acid? It turned into this molecule. And if it grabs an H plus, it could go back. So this is actually the conjugate base. Another, I know it's not a reversible reaction, so it's hard to predict what happens if it goes backwards. Here's another idea. We have to memorize this as an acid. So its conjugate must then be the opposite, the base. Okay, so this thing, bisulfate, is the conjugate base of sulfuric acid. Hydronium, well, what was this thing? Water? It is water. What is it doing in the reaction? It's acting as a base. Okay, so this thing is a base, so its conjugate must be the opposite. It's the conjugate acid. Cool. All right. There's still a second hydrogen on the original sulfuric acid molecule. That comes out partially. It doesn't fully ionize. It's not a strong electrolyte. So if you add, if you watch this bisulfate ion, what does it do? It's not very strong of an acid by itself. We now get a reversible reaction. It's a weak acid. But it can still donate its second hydrogen. It goes to the water, and then bisulfate then becomes sulfate ion. And you create a second molecule of hydronium. Cool. And then what kind of conjugate is this thing? Well, we started with an acid, therefore this must be the conjugate base. Yep. Cool. Water's still the conjugate acid of, sorry, water, no, hydronium, sorry, hydronium is still the conjugate acid of the water molecule. In this case, water's acting as a base. Okay, I think we're good on that. Let's take a look at some bases now. Oh, and I also put this note just to remind myself, in case I didn't say it earlier. Yep, acids, both strong and weak, usually list the hydrogen atom first in their chemical formula to identify them as acids. We'll have to memorize a list of 6 to figure out whether it's a strong or a weak acid. If it's not one of the 6 that we memorize, then it must be weak. Okay, the list for acids, the list for bases is easier, I think. There are strong and weak bases. The strong ones contain hydroxide ion. With the alkali metal, so you get your periodic table and see that's Li, Na, K. There are other alkali metals, but they're less common, so not to worry about those. Or the second column, the calcium, strontium, or barium. Those are your strong ones. If not on the list, that must be weak. So there are others like, I don't know, copper hydroxide or tin hydroxide, whatever. They don't fully ionize. They're insoluble. Ooh, solubility rules. Yeah, these are actually somewhat insoluble too. So that's kind of questionable, huh? Anyways, yeah, let's not go there. Other molecules of an OH group will be bases, but we can also have carbonate ions. So if a molecule has a carbonate ion, that's going to be a weak base. And then we'll add to that list molecules that contain a nitrogen atom where that nitrogen has a lone pair of electrons. So a very common base, weak base, is ammonia. So if you have any ammonia cleaning agents in your house, that's because it's a weak base, and the cleaning agent is using some acid-base chemistry to do some cleaning, some dissolving of dirt and other materials. Okay, and then I just put in the lone pair. What's important about knowing the lone pair is that if I say, hey, nitrate, are you a base? You have a nitrogen atom. Ew, it turns out nitrate doesn't have a lone pair. So we'd have to draw out all the electrons, the Lewis dot structure to see that. But a better way to remember that it's not a base is that HNO3 is a strong base, right? One of the ones we had to memorize. It's a one-way reaction. All of the nitric acid molecules form H+ and NO3-. And the NO3- doesn't react backwards. That's what makes it strong. This fully ionized, and then it stays ionized. Nitrate has no desire, if it's a thing, it doesn't have really feelings, but this entity, this ion, doesn't want to grab an H+. It doesn't want to accept it and go backwards. It doesn't want to reverse the reaction. It's not a base. That's probably the best way to know that this form of nitrogen, which is pretty common, is not a base, even though it has an N. The reason why it's not, I guess 2 reasons why nitrate is not a base. 1, if you draw out the Lewis dot structure, nitrogen doesn't have a lone pair of electrons. And 2, it's the conjugate base of a strong acid. And even though it has the name conjugate base, it's not basic at all. I know, it's a little misleading. Wait, we're calling it conjugate base. Doesn't that mean it? No, it doesn't. Darn it. Okay, let's see some examples of these in acid-base reactions. Well, let's grab the ammonia. NH3, you put it in water. So water's around, that can serve as a reagent then. And NH3 is not a strong base. It's just a weak base. Not on the list. Well, the list is just molecules with hydroxide ions and these cations. So then it's a reversible reaction because it's weak. Reaction reverses. Okay, what happens? Well, we just said this is a base. So what do bases do? They accept H+. So, hey, nitrogen, want another H+? Sure. You start with 3, you greedy little nitrogen, and now you have 4. And that H+ came over with a positive charge. It's still there because ammonia was neutral. And you get NH4+, which you should recognize as the ammonium ion. All these polyatomic ions showing up. Yeah, they're pretty common. That's why we're asked to memorize them. Okay, so that's one product. Water, what are you doing? Well, the base, a weak base, is accepting H+, so I guess that comes from you. Yeah, the H is listed first. So you're going to be the acid, but you're not on the table of 6 strong acids, so you must be a weak acid. Yes, go donate an H+. Hey, water, oxygen, you first had 2 H's, now you don't. You only have 1 H. And water, you were neutral and you kicked out something positive. So now you're more negative. Yeah, you turned into hydroxide ion. Which, is that an acid or a base? The strong acids contain hydroxide. So hydroxide itself in solution acts as a strong base. It is a base. And if you wanted to, you could say, hey, water, what's your conjugate base? It's hydroxide ion. Hey, ammonia, what's your conjugate? Well, ammonia is a base. So this molecule must be the conjugate acid, right? The conjugate's the opposite. So NH3 is a base, so its conjugate must be the acid. Well, now this reaction is reversible. So let's get our point of view focused on the ammonium ion and see what becomes of it when the reaction goes backwards. Okay, so start with ammonium and hydroxide and ammonium, you're nitrogen with 4 H's, and then you go backwards to become NH3, and you're missing an H. What'd you do? It donated it away. And that's the definition of an acid. You donate it away to who? To the strong base, who just ripped it right out of your hands of, nitrogen. Hydroxide ion accepted H+. That's the definition of a base. And hydroxide took another H. So now oxygen has 2 H's. The H came over as a plus to cancel out the minus, and we're left with water. Cool. Well, why don't we do all the bases? We had hydroxide ion, we got carbonate and ammonia. I went with ammonia first. Oh, just to give you some other ideas of some other bases containing nitrogen. A common tactic is that, hey, let's draw the Lewis dot structure over here. So here's ammonia, 3 H's. One strategy is to take off a hydrogen and put on a carbon. And then, do you remember how it times carbon bonds? Well, remember the little HONC acronym? HONC, honk your horn, 1, 2, 3, 4. Carbon prefers 4 bonds. Hydrogen and the halides prefer 1 bond. So if you put on a carbon in place of a hydrogen, this carbon is going to need a total of 4 bonds. So maybe you put hydrogens here. And now you have another base, another weak base. And you can do that to all the hydrogens if you want, or just 2 of them. Why do you have to just put on 1 carbon? You could put on a chain of carbons. Anyways, that's a common way to see a whole bunch of different bases. Just have somewhere in the molecule, there be a nitrogen with a lone pair. And really it's like if you like math, it's a derivative of ammonia, meaning these bases were derived or came from the ammonia molecule. All we're doing is substituting out the hydrogens for some carbons. Okay, cool. Let's see a reaction with hydroxide ion. I probably should have done that one first. What if we have calcium hydroxide? That was listed as one of our strong bases. This actually would come in as a solid. And then I should have muted my phone. Okay, so we know this to be one of the strong bases. And then, hey, why don't should we use this acid here? It's right there. Why not? This is a conjugate acid. It's a weak acid. It's not one of the acids we have to memorize. It's not one of the 6. So let's predict the product. And then we'll have to balance this. I forgot about checking to see if things were balanced. I believe everything has been so far. Should have checked. This one's not, because we got 2 hydroxide ions. That was my big clue. It's like, wait, each hydroxide ion is going to need an H+. All right, let's predict the products. We kind of already said it. Each hydroxide ion needs an H+. And from this reaction, we know that the ammonium ion can release an H+ and turn back into ammonia. So you might say, well, this is one of the bases I had to memorize, so this thing must be the acid. And the definition of an acid is that you have to donate H+. So, hey, nitrogen, let go of one of those H's and let the H take off with the plus charge. Donate the H+. So then NH4 ammonium ion, you're going to turn into ammonia. That's going to be aqueous. And then this gets a little weird. This is a solid, but once it dissolves in water, it forms calcium ions and hydroxide ions. Okay, let's predict the product and worry about balancing later. So I know there's 2 hydroxide, we'll just focus on 1. 1 hydroxide, you're the base. You go grab an H+ from the ammonium ion, and once hydroxide has an H+, that turns into water. Water's a liquid. And then the last product is, well, what's calcium? It's just a +2 cation. I know this is a weird looking reaction. Need a little more room. There we go. Cool. All right, so we predicted all the products. Now let's balance it. Save the simplest molecule for last. So among all these things, who's the simplest looking? Calcium, a single atom or ion. Okay, so don't balance calcium first. Go after the N, the H or the O's. And maybe nitrogen. Okay, nitrogen looks balanced already. Good. Want to try the H's? There's 5 of them here. There's only, well, there's 2 here, and there's 4 here. That gives you 6. Well, we're just 1 off. Can we just add? Well, there's a guessing game. And if you ever run into that predicament, you can make a guess and keep moving forward. But you know what? You don't have to balance a hydrogen next. Why don't we go after oxygen? That actually is a better idea. So that's a good strategy. If you get stuck like I did, it's like, well, I can make a guess. No, let's just balance something else first. That's a better strategy. Okay, let's look at the oxygen. Ooh, there's only 1 oxygen on the right side, but there's 2 oxygens over here. Okay, I know how to fix that. Let's put a 2 in front here. Now there's 2 O's. And now let's go back and check the hydrogens. I got 4 here and 3 is 7. I have 2 and 4 is 6. Darn it. Okay, what else can we do? Got the O's, got the N's. The only thing I can do, I thought I was going to save calcium for last. Thinking a little chemistry. I'm trying to think of strategies for you. Why don't we go back to this? There's 2 hydroxide ions. Each one needs an H+. The ammonium ion can only release 1 H+. So there's 7 H's over here. There's only 6 over here. Why don't we double up the ammonia molecule so that now there are 8 and 2 more is 10. And I messed up the nitrogen. Nitrogen is not balanced. So let's fix that, putting a 2 here. Okay, now, that was a tricky one to balance. Now things should be good. Let's double check. Nitrogen, there's 2 on each side. Hydrogen, I got 2 H's here, and I have 8 here for a total of 10 hydrogens on the left. I got 2 times 3 is 6. 2 times 2 is 4. Now there's 10 H's over here. I got 2 oxygens. Yep, 2 oxygens, and 1 calcium, 1 calcium. Cool. All righty. We got balance. Oh, let's match up conjugates. So we got our strong base here, and it's really the hydroxide ion. So hydroxide ion, what did you turn into? You turned into water. So water is the conjugate what? Well, hydroxide is a base, so this must be the opposite. It's the conjugate acid of hydroxide ion. Cool. What about this? Well, this is an acid, so the ammonium ion turned into ammonia, and NH3 is the conjugate. What is it? Opposite of the acid. It's the conjugate base of NH4+. Why is this a one-way arrow? Because this is strong. It's not going to go backwards. Cool. I think we've fully broken this down. Last one, let's look at carbonate. Checking my notes, make sure I'm not leaving something else. Ooh, there's one more idea after we looked at carbonate. I like calcium. What if we have calcium carbonate? No, calcium hydrogen carbonate. Yeah. Okay, so I said I was going to use the carbonate ion. But carbonate's hiding inside the bicarbonate or the hydrogen carbonate ion here. You need 2 of those to balance the charge, right? Because bicarbonate has a -1 charge. Calcium's got a +2. You're going to need 2 of these to balance the charge. And I want carbonate to act as a base, so I need to add an acid. Let's use a strong one. How about hydrochloric acid? Comes off the list. We recognize a strong acid, and that makes this one a weak base. It doesn't contain hydroxide ion, so it's not a strong base. Okay, what do we got as a product? Well, I'm gonna do the easy one first. Hey, acid, what's your job? Donate H+. Well, HCl, you got an H, go release it. Kick out something positive, what's left behind must be negative. So HCl turns into chloride ion. Oh, it's a one-way reaction because this one's strong. So if one of your acids and bases is strong acid or strong base, it's going to be a one-way reaction. Then what? Well, what became of the H+? It paired up with your base. And I know it's not strictly speaking carbonate, but it's hiding in there. Bicarbonate is also a base. The H is listed first. So sometimes bicarbonate can release an H+ and act as an acid. Maybe I should do that one next. We should. We'll take a look at that. Go. H+, you come over here, and you're the base, bicarbonate. So here comes another H. You had one. You now have two. Ooh, a little red flag went off. We'll do something with this in just a second. Okay, then what do we have here? We got two of these. So we're gonna have to think about two of these reacting. Each bicarbonate, these an H+. So I'm already thinking about putting a 2 here to balance it. What became of calcium? It's a spectator ion. It's not doing anything. If you wanted to, you can pair up these counterions and make a salt. Maybe we should do that in a second. But first, let's go back here. This is carbonic acid. So way back in some previous video when we introduced carbonate, I know carbonate is this ion, but bicarbonate is very similar, reacts the same way as a base, and that is carbonic acid, H2CO3 is unstable, and it falls apart to form water, which is a liquid, and carbon dioxide, which is a gas. So Alka-Seltzer fizzes because there's some carbonate ions that react with an acid in an Alka-Seltzer tablet. In water, it produces carbonic acid, and ultimately carbon dioxide, which is the fizz. This is a gas that starts creating bubbles. So more space, please. Let's rewrite what we got so far. We got calcium bicarbonate. Maybe we start as a solid. And we add HCl, and we're already thinking probably 2 hydrochloride molecules because we have 2 bases hiding in there. And chloride ions, and water, and carbon dioxide, and calcium. Okay, and then let's balance this. Okay, supposed to find, save the simplest for last. So the chloride or the calcium is the idea, but we ran the problems before. So let's fix that by just balancing the acid-base reaction first. We said that bicarbonate, HCO3 minus, except an H+. And because there's 2 of them in here, let's already provide 2 H+, 1 for each of the bicarbonates. Cool. Okay, and then let's just start checking things. How many calciums do we have? 1 of each. Cool. How many hydrogens do we have? I got 2 here, and 2 more is 4. Well, I only have 2 over here, so why don't we put a 2 there? So hydrogen's balanced. I guess I'm saving chloride for last. Oxygen, there's 6 oxygens here. How many over here? I got 2 there, another 2. Darn. Okay, so maybe I have to add, well, I was going to just change this, but you might be thinking, why don't you change the water? Because that has oxygen too. So to get more oxygens over here, either one of these molecules we changed. And so in my head, I said, I'm going to forget about the oxygen in a second. And let's go look at carbon. That'll help. There's 2 carbons here. No carbons there. So there's 2 carbons on the left side. only have 1 on the right. So yeah, definitely make that a 2. And now let's go back and check the oxygens. I got 4 oxygens here. 2 more is 6. And we started over here with 6. Good, oxygen's balanced. I didn't mess up the hydrogens, right? There's still 2 plus 2 is 4. Yeah, I still have 2 times 2 is 4 here. Good, calcium, you're good. Carbon is good. Chloride, you're last. There's 2 chlorides here, so give you 2 more. And then that's done. Some scientists might want to simplify this reaction a little bit. And say, hey, you have some anions and some cations. They should probably pair up and form a new material, a new salt. So 2 chlorides and 1 calcium. Hey, that's just enough to balance the charge to form some calcium chloride, which should be dissolved as ions. So if you want to leave it in this form, perfectly acceptable to me. Someone else might say, well, you're going to get these calcium chloride molecules in there. So you could write it like that too. Okay, I think we're good there. It's all balanced. Oh, we should probably match our conjugates together, right? Well, HCl is a strong acid. So where's its conjugate? Well, it's hiding as chloride. It's really here. Chloride is the conjugate what? Well, HCl is an acid, so chloride is the conjugate base of HCl. But it's not a base, a little misleading. Chloride does not want to pick up an H plus and go backwards. HCl is strong, it only donates H plus and then it's done reacting. Bicarbonate, what became of you? You turned into, ooh, guess carbon dioxide. So carbon dioxide, you must be the conjugate. Conjugate what? Well, let's go back and ask over here. HCO3, what did you do to become CO2? You're missing an H. You donated H. Who donates H's? Acids do. Whoa. But that's because it fell apart. Darn it. All my nice little rules and definitions. Chemistry, full of exceptions. We kind of have to go back up to here. What became of bicarbonate? It became carbonic acid. So CO3 had 1 H, now it has 2. So before it fell apart and lost all its H's as water, it acted as a base. Darn it. Yeah, so bicarbonate, you're a base, mainly because HCl is a strong acid and just dominates, forcing the other molecule to be the base. Okay, this is the base, making CO2 the conjugate opposite, the conjugate acid. Yeah. Weird stuff. I think I said I was going to do carbonate, what we just did. Hope I did everything. Oh, there's one more idea. One more term, right? Bicarbonate. Here it's acting as a base. If you write the net ionic equation, it would look like this. Well, it's not the full net because we have other changes, but here's, if you're only focusing on bicarbonate and its chemistry, here it acts as a base, grabbing H plus to form carbonic acid, which then decomposes to form water and carbon dioxide. Bicarbonate, however, can also act as an acid. If you throw in a strong base, hydroxide ion, now hydroxide ion says, hey, give me that 1 H you have. Hydroxide turns into water with the extra hydrogen, right? Add an extra H plus to the O becomes water, liquid. And then bicarbonate, loss of hydrogen, now it's a carbonate ion, which has a -2 charge. Yeah, so this one molecule acted as both an acid and a base. We saw that before. Is it right over here? Yeah, here's water acting as a base. And then water, here it is. Water is acting as an acid. So water can do this thing where it's either an acid or a base. And not only water, but bicarbonate. So if we want to write a Nettach equation there, we could say, hey, water, if there's a strong acid around, water will be a base, form hydronium ion. And if water is around, when there's a strong base, like hydroxide ion, then hydroxide will grab the H plus and turn it into hydroxide ion. And then hydroxide will grab that water. Yeah, my handwriting got horrible there. Anyways, water is acting as a base, acid and base, bicarbonate is, there's a name for that phenomenon. We can say that these molecules are both amphoteric. Let me make sure I'm spelling it right. That always reminds me of amphibians. Amphibians that can live on land and in water, they can do both. So amphoteric means they're both an acid and a base. So it reacts as either an acid or a base. And that is plenty for now. Yes, that's everything on my notes. I'll see you in the next video.